Dear learners, greetings from IIT Guwahati. Welcome to this course Fundamentals of Compressible Flow. We are in the last module, that is module 8. The title of this module is Measurement Diagnostics and Experimental Facilities for Compressible Flow. Till this point of time, we have been studying all the theoretical backgrounds involving shock waves and expansion waves. Now, we will try to see that if we have a compressible flow situations in the laboratory, what are the measurement facilities that are available, first point. Second point is that if at all we develop this facility, how you are going to measure the conventional parameters like pressure, temperature, density and so on. So, while talking about experimental facility, I assume that normally when you deal with missiles or high speed vehicles or space shuttles, aircrafts traveling at high altitude, the main idea behind them is that we have to simulate those flight conditions. That means, we have to simulate the different altitude conditions in the laboratory. So, in that way we have many facilities are available and also we have to make it reality. And side by side when you develop these facilities, we also have to ensure that many fluid mechanics parameters such as pressure, temperature, enthalpy has to be either measured or they have to be derived. So, this is the basic philosophy of this module and we will touch upon some of the important concepts and preliminary concepts on measurement diagnostics, and subsequently we will see that how those measurement diagnostics can be used for experimental facilities. So, in the first lecture I will touch upon the classical measurement techniques, and under this heading we are mainly focusing on temperature measurements, pressure measurements and velocity measurements. And main challenge behind them is that all these pressure, temperature, velocities are very common phenomena in the incompressible flows and they are dealt with very precisely. But when you deal with those measurements in the compressible flow domain, then there are many challenges that are involved, because speed is very high and your sensors must be accurate enough or fast enough to respond the flow characteristics. So, this is the main theme of these lectures, and towards the end of the lecture we will try to solve some numerical problems. So, let me start the first segment, that is what are the measurement challenges that we encounter in compressible flows. So, when I say compressible flows, from the very beginning we say it is a variable density flows. So, the measurement techniques that are incorporated in liquids which are incompressible are not applicable for gases, because they cross the incompressible limit, because we have already discussed all the theories for which the compressibility effect is high and Mach number of the flow is higher than 0.3. The pressure gradient causes the predominant change in the velocity, keeping the density constant for liquids, but on the other hand the main important factor is that the pressure gradient in the flow leads to substantial change in the velocity as well as density. And so, we say that compressible flows are variable density flows for which the density change is higher than 5%, and this density change occurs mainly due to pressure gradient. So, till this point of time we have seen the shock wave formations, variable area passage, heat exchange, frictions are few mechanisms that can change the density during the flow. So, these are the what we say the classical features, and to capture this flow phenomena we require advanced measurement techniques which is mainly used for supersonic and hypersonic flows, and they mainly rely on density information during its motions. The very basic fact is that we have to take the advantage of density change. That means, if you are able to change the or if you are able to change the acceptance of density during the flow field through some techniques, then we are done with the measurements in the compressible flow. So, this is the very basics and fundamental aspects. So, as you see these two equations here, the densities are for liquids pressure is a function of density, but in a very rare sense, but whereas the for gases it follows the equation of states in which density can be altered by pressures easily, as well as you can also change the temperatures. So, till this point of time we have seen many theories in this compressible flow. We have seen normal shock, we have seen oblique shocks, we have seen expansion waves, and for all these things there are theoretical backgrounds are available. And side by side, when you say that in a one dimensional duct, if a heat is added in a supersonic flow or in a subsonic flow, we can say that there is also a possibility of density change. So, this is what we say compressible flow with heat transfer. The other mechanism of change in the density is also due to frictions. That means, if you have a certain length of duct, that is a subsonic flow and supersonic flow, then what we can have is increase or decrease in the length of the duct could alter the change in the density. So, these are things that for which theoretical backgrounds are available with us, and we will have to take the advantage of those theories, and side by side we can do some basic measurements and by which we can define the complete flow fields in the compressible flow. Okay. So, when you talk about the measurement challenges, again there are two components of measurements. One is pressure and temperatures in the flow field, and these temperature and pressure measurements are nothing but the localized measurements. Basically, wherever it is required, we can insert a probe and start digging into the pressure or temperatures, and by doing this pressure and temperature measurements, we can use this compressible flow theory to calculate, or we call these as a gas dynamic relations. Those gas dynamic relations can be useful to calculate all other parameters. And in fact, when we are dealing with compressible flow situations, what may have is that, and in particular if the flow is supersonic or hypersonic, for example, in this particular case there is a compressible flow in which flow is supersonic, and where a probe is inserted, it could be a pressure, temperature or any other thing. When it is inserted, there will be a shock waves that is always going to happen. So, when we are actually doing the measurements, these measurements is performed, and of course, there are boundary layers also that are possible in addition to the shock layer. So, whatever measurement we do, we have to remember that these measurements are performed within the shock layer or boundary layer, and these really do not depict the correct flow fields. So, from these measurements and looking into effect of shock and boundary layer, we have to get back the entire flow field informations. So, that is where the challenge is required, and we need some advanced measurement techniques such as flow visualization techniques through optical methods, and all sorts of things are now recent updates in which one can make the measurements of complete flow field in high speed domain. So, let me start the first measurement, that is localized measurement of temperatures. Now, when I talk about temperatures in a compressible domain, we rely on either static temperature or stagnation temperatures, and they are and both the parameters are defined for a particular Mach number. And in fact, static temperature and stagnation temperature is related with respect to Mach number in an isentropic flow. Now, the next question is that how to measure those temperatures. Normally, the static temperature is measured by a device without disturbing the flow. So, for example, if you look at this particular picture, there is a compressible flow, that is in which any arbitrary flow for which the free stream pressures are P infinity, T infinity, and total pressure is T naught and Mach number is m, and it is flowing over this, and we can see in that thing we have a boundary layer, we have a shock layer, all these things are there, and on top of that we are measuring a putting a thermocouple which measures the temperatures. A clear picture we will see here that if you have a flow coming in these directions and we have a very concise thermocouple or probe that takes a sample of flow into it through this converging passage, and actually the thermocouple which is probe stands here, it takes this flow which comes through this channel. Now, here and accordingly we do the measurements. Now, when you do the measurements, typically we may have land of a shock layer, we may land of a boundary layer, and whatever measurements we do, we say the measurements is temperature is measured by T_p, but whereas our temperature are measured by the probe, whereas the actual temperature which is stagnation temperature of the flow can be taken as T0, and free stream temperature can be T infinity, and this refers to a Mach number m. And when you deal with this shock layer and boundary layer, and typically when you deal with the boundary layer, we can also have a situations that there will be a temperature profile that gets built up within the boundary layer, and of course, if you superimpose this velocity boundary layer, we will have velocity gradient starting from the bottom and it goes to top, where velocity is 0 at the bottom and it goes to free stream at the edge of the boundary layer. And similarly, temperature profile will have the maximum temperature which is the which we call this as adiabatic wall temperature, and more details we will see later, and this is what we call as adiabatic wall temperature, and starting from this we will have another temperature and finally it merges with the free stream. So, the very basic philosophy that although you have true value of temperature T0 and T infinity, but we have so many other temperatures that has popped in. One is the temperature measured by the probe, other is the adiabatic wall temperatures, all sorts of things are coming into pictures. So, we must precisely say that what temperature we are actually measuring, and this is the challenge here, what we call as a temperature measurements. And typically the temperature measurements are normally done using the thermocouple. However, the conventional thermocouple and high speed than the thermocouples that are used in the high speed environment, they are quite different, and that is based on their sensitivity values. And typically if you look at a thermocouple, it works on the principle what we call as Seebeck principle. What it says is that flow of heat in a metal always induces an electrostatic force and generates a voltage change with respect to temperature change. If you have a similar metal, when we have a temperature difference, there is a heat flow due to a heat flow, and there will be current will be induced. And side by side, if you have a dissimilar metals, then the current flow will be reversed, and both the metals they are joined, then we can have a closed circuit involving a EMF E. So, basically when two metals that is similar and dissimilar metals are joined together to form a circuit and EMF is generated. So, by quantifying this EMF we can measure the change in the temperatures. Now, based on this combination of the materials, it could be chromel, alumel, chromel, constantan, copper, constantan, and there are so many things, and based on this they have also a temperature range, and they have their sensitivity also plays a very vital role as far as the thermocouples are considered. So, the very basic principle is that this thermocouple can be prepared by joining two dissimilar metals at 2 points. One junction is kept at a place where the temperature is measured, while other is the one where we call this as a reference junction. Okay. Next important aspects of this temperature measurement is the Prandtl numbers. So, if you recall our heat transfer theory, the Prandtl number is a non-dimensional number, and that is mainly used to study, and it is a basically non-dimensional number, and that is defined by mu Cp by K, where K is your thermal conductivity and mu is the viscosity. So, it is a basically basically involves the heat transfer due to viscosity effect and heat transfer due to conduction effect. And the relative advantage of the relative weightage of these two will say that which is more dominant. For example, if you say Prandtl number is high, means that we expect that viscosity effects are dominant. If the Prandtl number is low, we can say conduction effects are dominant. And in fact, for gases this Prandtl number is low. So, we say that conduction changes are dominant. Now, let us see in our measurement philosophy why this Prandtl number is important. So, if you look at our viewpoint of measurements, that we are actually measuring a temperature from a probe which is in a compressible domain, and this measured data is based on the measurement performed within the shock layer and boundary layer, and for which the true values of pressures temperatures are static temperature T infinity and total temperature T naught corresponding to the Mach number m. Now, we have to say that whether you are able to measure actually T naught or something else. So, that is the question mark. So, when you see this aerodynamic viewpoint, the gases passes over the probe, there is a velocity gradient within the boundary layer, and this gives rise to shear stress resulting fluid friction and heat dissipations within the boundary layer. So, in a sense that when such effects are happening, then the probe is expected to feel a temperature which is above the stagnation temperature. And side by side, the temperature gradient in the boundary layer also gives rise to heat loss from the probe, and this has a opposite effect to the fluid friction. So, in one way fluid friction increases the temperature, other way is that the probe tries to lose the heat. So, these two contradict phenomena we can judge this by this factor Prandtl number. For example, when you perform the measurements, the thermal conductivity of the probe plays vital role, because when we are doing this for gases Prandtl number is less, and so conduction effects are very predominant when you are actually dealing with the probe. That means, value of K is very important. We have to restrict it in a sense that we have to take appropriate measure in terms of heat loss due to conduction. So, when I say heat loss due to conduction, then we must insulate the probe. Now, when we insulate the probe and when this probe is kept in the flow field, so typically the insulation is made when a probe is kept in the flow field and we have kept insulation from the side and there is a flow coming into it. So, we say this insulation, and this probe has wires, and these are nothing but the connecting wires. However, we must expose the sensing surface of the probe to the flow. So, the effect that by insulating from the sides, we restrict that no heat transfer from the side, but however, we ensure that whatever heat transfer that comes from the flow has to be sensed by the sensing surface. But in a sense that there is also a possibility during your time scale of measurement, there could be heat loss through these connecting wires. So, this heat loss is, we call this as a conduction heat loss, that has to be limited. So, to counter all these facts, the first parameter we are going to define what we call as a adiabatic wall temperatures. So, ideally speaking, that we have to restrict the probe to other modes of heat transfer by putting an insulation from the side, but only idea is that only the sensing surface must expose to this flow. So, based on that we define a parameter what we call as a adiabatic wall temperatures. So, when a thermocouple is located on the wall of the surface inside the boundary layer, the flow velocity is 0 and there is a temperature gradient. When you put it, we say dt by dy is equal to 0, that means we have at y is equal to 0, then we say that when the probe is insulated. So, the measured temperature on the wall would be closer to the total temperatures, but still we have not taken into account the conduction effect due to the conducting wear. So, in one sense that we restrict the heat transfer from the sides by insulating it or through protection of through this insulation protection. And if you do that, if your true value is T naught and we were going to measure a closer value of that of T naught, which we call as TAW, and we call this as a adiabatic wall temperature. So, instead of measuring T naught, we are actually measuring the adiabatic wall temperature. So, based on the concept, we define a parameter what we call as adiabatic recovery factor, means that if your true value of stagnation temperature is T naught and corresponding static temperature is T infinity, but the probe that measures is the adiabatic wall temperature by putting insulation, then the ratio of difference between these two parameters, that is R is equal to TAW minus T infinity divided by T naught minus T infinity, will give you the value what we call as a adiabatic recovery factor. And based on that, your main equation gets modified. So, if you see your true equations of T naught and T infinity as a function of m is this, that is T naught by T infinity is equal to 1 plus gamma minus 1 by 2 m square. So, by including this adiabatic wall temperature, the equation is now changes to this TAW by T infinity is equal to 1 plus R into gamma minus 1 by 2 into m square. So, this is what we call as adiabatic wall temperature concept, and ideally this value of R recovery factor is nothing but a function of Prandtl number, and this R is equal to PR to the power half, that is for laminar boundary layer, R is equal to PR to the power 1 by 3 for turbulent boundary layer. Now, next parameter we are going to define what we call as probe recovery factor. So, as I mentioned that when your actual condition is T naught, that is true condition, and T infinity, that is stagnation and static temperatures, but the probe actually measures Tp, that is temperature of the probe, and there are connecting wires which is taken from these ends of the probe. So, these connecting wires incurs losses due to conduction during the time scale of measurement. So, in a sense that is it possible to make the measurement close to the stagnation value by restricting the losses due to the connecting wires? By assuming this fact, we define a factor what we call as probe recovery factor, and that is nothing but K is equal to Tp minus T infinity divided by T naught minus T infinity. So, that is what we call as a probe recovery factor. So, the stagnation probe is employed for measurement of total temperature in the absence of wall. The flow is slowed down to 0 velocity at the thermocouple with no gain or heat loss. A typical design employs vent holes to allow proper ventilation or seals or thin lead wire to minimize heat conduction loss. So, in such a situation, it is possible to measure the probe temperature, that is Tp, which is slightly below the true value of stagnation temperatures. So, based on that we find a parameter called as probe recovery factor, and this by suitable design and proper calibrations, its value can be close to the unity. So, this is how the significance of probe recovery factor. So, now if you summarize the whatever temperature measurements you have studied and try to see the temperature versus velocity plot. Now, the temperature velocity plot, if this refers to the static temperature that drops with the velocity, but the total temperature remains same T naught, and what the probe measures, its trend is something like this. That means, at one particular velocity it has very least effect of conduction and radiations, and it is close to the stagnation value. Now, if the probe is properly insulated from the sides, its adiabatic will follow a path what we call as TAW, and the difference between these two we call this as a velocity error, and also due to the calibration error we can say it is a conduction or radiation error due to the stem of the probe, and this also has to be done at different velocity during proper calibration process. And different expressions that are used here: total temperature T naught is equal to T infinity plus B infinity square by twice Cp, and T naught by T infinity is a function of Mach number. This adiabatic recovery factor, which is a function of TAW, T naught and T infinity, and recovery factor of the probe is a function of Tp, T infinity and T naught. So, for temperature measurements these three things are very important. Now, we will move to the pressure measurements. So, conventionally the pressure measurements and is another approach which is used most frequently, and when you dealt with incompressible flow we are aware of a concept called pitot probe measurements. This pitot probe handles the measurements and we call pitot handles the measurement in which the simultaneous measurement of static as well as stagnation temperature is possible. So, just to give the very basic concept of static and stagnation measurements, I can say that if you have a flow directions and we try to look upon the pressure measurements where the sensing surface of the probe is parallel to the direction of the velocity, then we say the measurement is static measurement. Now, when the sensing surface of the probe is perpendicular to the direction of the velocity, or plane of this probe is direction of the velocity is perpendicular to the direction of velocity, we say it is a stagnation measurements. And this is the very basic difference that we see that during static and stagnation pressure measurements. Now, with respect to compressible flow field, the measurement concepts of static and stagnation pressures are equally important. When the measurement is made in such a way that velocity is not disturbed, the indicated pressure would be a static pressure. On the other hand, if the velocity is brought to rest isentropically, then the measured pressure will indicate the stagnation pressure. And there is another picture which is gives more clarity. So, if you have a stagnation hole that you have to project it in this manner, and in which it should disturb the flow, and if you have a static probe we have to insert in such a way that the flow is not going to be disturbed. And when both the concepts are merged together, then what we have? We have designed a probe, and this probe we call this as a Frankel-Pitot static probe. That means, it gives the simultaneous measurement of static pressure as well as stagnation pressure. How? If you look at, if you insert this particular probe into flow fields, and there are one sensor that is mounted at the nose of this probe, or there are multiple sensors which is mounted on the circumference, and which are there equally spaced holes. The plane is perpendicular to the flow, and the flow that goes along these directions, this particular sensor sees the static pressure of the flow, and both these things, both the wirings are taken together. One is from the static holes, other is from the stagnation holes, and they are sent it to data acquisition systems for recording the data. So, in a given probe, what we call as Frankel-Pitot static probe, it is possible to measure simultaneously the stagnation as well as the static pressure. Now, let us see that when you deal with the pressure measurements, and if the flow is subsonic, what is going to happen? If the flow is supersonic, what is going to happen? So, this particular things what as I mentioned earlier, if you insert a Frankel-Pitot static probe, we are able to measure static pressure and stagnation pressure simultaneously. But one thing is that if the flow is subsonic, then you are ensured that there is no shock wave, and whatever data we get, that is actually the true value of two replications of total pressure and static pressures. So, if you have this particular probe if you have the true value of pressure is P naught, that is stagnation pressure, and corresponding static pressure is P infinity. The static pressures which is mounted on the circumference will sense the value of P infinity, and this particular sensing probe which is mounted here, it will talk about P naught. So, in a sense that if the flow is subsonic, because there is no shock wave and we can easily replicate the total value total pressures using this pitot static tube probe. But what happens in a supersonic flow, since this particular similar probe is mounted in this manner, we will have a shock wave, and that shock wave will be, because since this shape is a blunt in nature, so we will have a shock wave, and this shock wave will be a detached shock and standing at certain distance delta. And so, whatever measurement we are doing from this probe, we have to remember that this is the conditions which is and if you assume this to be a bow shock and close to a normal shock value. So, if your initial condition is P naught 1, P 1 corresponding to Mach number M 1, the measurement is performed in the region 2. We say the measured pressure will be P naught 2, and this measured value of pressure will and the Mach number will decide what the true value of stagnation pressure. So, we have to recall our compressible flow theory normal shock relations, for which the ratio one is isentropic relations, in which is stagnation pressure to static pressure relation as a function of Mach number. Other is the ratio of stagnation pressure after the shock to the static pressure before the shock as a function of free stream Mach number. So, we have to use this equation judiciously, and in addition to that we can use the normal shock table to find this ratio, and based on this ratio we can revert back to the information of Mach number and subsequently for other data. So, this is the very basic difference that what when you measure pressures for subsonic and supersonic flows. Now, in addition to that, there is another parameter what we call as a flow velocities. So, the flow velocities are normally not measured for compressible flow, rather they are derived from the measured data of static pressure or measured data of static or stagnation pressure or static or stagnation temperatures, because gas dynamics relations are available. But however, for incompressible flow, as I mentioned, the difference in the pressure of is between the static and dynamic pressure will be give you the difference between the total pressure and static pressure will give you the dynamic pressure, and this dynamic pressure relates to the flow velocity. But in a compressible flow, if you know the Mach number, from this Mach number and speed of sound relations, we can get back to the information of velocity. Now, we will try to solve some numerical examples how this velocity can be measured for a subsonic and supersonic flows. And now, in the last part I am just to touch upon some important concept that normally we come across Bernoulli's equations, and this Bernoulli's equation is a very common phenomena when you use it for an incompressible flow. A common question that comes in or drops in, that does this Bernoulli's equation applies for a compressible flow? The answer is typically yes, because if you look at the general expression dP by rho plus B dB plus Gz is equal to 0, this is the differential form of equations, and here when you deal with the incompressible flow, we keep this rho as a constant and integrate this. Now, when you integrate this, we say P plus half rho B square plus rho Gz is equal to constant, and this constant can be related that for a given situation, if you make the measurement to be 0 with 0 elevation, the total pressure that is measured can be correlated to the stagnation pressures. So, this constant can be correlated with the P naught. So, for this is what we do it, and from these informations That means, if you have stagnation pressure, if you have static pressures and if you have fixed density, we can get the flow velocity. Now, let us see if this particular equation whether we can use it for compressible flow or not. Now, for a compressible flow, you can recall our isentropic relations P v to the power gamma is equal to constant, and by here the main thing that what we are going to do is that we have to find this dP by rho as a fixed parameter. So, that means pressure with density change you have to do that. So, if you can differentiate these equations dP by d rho, then from this equation we can find out this parameter dP by rho is equal to C into rho to the power gamma minus 2 into d rho. So, now if you integrate this, ultimately we will arrive at this particular relations. So, that is gamma by gamma minus 1 P by rho plus V square by 2 plus Z z is equal to constant, and the way we deal with this constant P naught here, this particular constant can be assumed that this constant can be related as gamma by gamma minus 1 P naught by rho naught. Since it is a constant and this has information of P naught and rho naught, that is total pressure and total density. And from this, if you can simplify, we will arrive at relations the information about velocity V infinity, which is nothing but twice gamma by gamma minus 1 P naught by rho naught minus P by rho and whole to the power half. So, if you look at this particular expressions of velocity in compressible flow and velocity in the compressible flow, the difference lies here that the density is a different parameter, and side by side we have another parameter 2s gamma by gamma minus 1, and this is nothing but the compressibility due to the effect of compressibility, and due to these effects becomes more and more predominant if the density change is high. So, this is what the very basic information that many times you get confused that whether a Bernoulli's equation can be applied for compressible flow or incompressible flow or not. So, this is what we say that it can be applied, but normally we do not go use those Bernoulli's equations for compressible flow, rather we have many gas dynamic relations are available with us. So, a good idea is to use those gas dynamic relations instead of talking about the Bernoulli's equations. And side by side, if you look at a close look, that if you make an incompressible flow calculations and compressible flow calculations, we can see that there is a significant difference. So, what we can say that the word stagnation pressure is normally a very common phenomena in a compressible flow, but it is not a common phenomena for incompressible flow, we rarely use, but there is a concept, that same concept can be used. Stagnation pressure defined for gases is not identical to the Pretard pressure defined for incompressible flow, where Mach number effects is not taken into account. The stagnation pressure calculated through Bernoulli's equations for incompressible flow effect does not take into account the compressible flow effect. That means, when you see use this Bernoulli's equations, the incompressible flow effect, there is this incompressible flow effect is there, that means we do not take into account the compressibility effect. So, from this if you see this gas dynamic relations, the static pressure to stagnation pressure as a function of Mach number, if you put Mach number is equal to 1, we will get the P naught by P ratio is 1.89. And in a similar sense, when you see this P naught by P ratio, by simply calculating the incompressible flow equation, that is through Bernoulli's equations, we will find that P naught star by P is equal to 1.7. So, what it says is that when the incompressible flow calculations will underestimate the stagnation pressure by 11% for sonic flow, and that means when you go up to sonic flow, the difference between incompressible or Bernoulli's equations and the gas dynamic relations will be 11%, but below that, but its effect can be seen when the Mach number is when you say Mach number 1, we say this inconsistent results will be 11%. When we say Mach number is equal to 0.3, that means we say compressible effect gets initiated which means that the Bernoulli's equation and gas dynamic relations will be close within the 10%, but below 0.3 Mach, there is Mach number below 0.3, there is no role of compressibility effect. So, this is the summary what I am going to say, that when you deal with the measurement velocity, to what accuracy we can go for these measurements. So, with this I will conclude this lecture. Now, we will try to solve some numerical problems based on our discussion today. The first problem it deals with the measurement of pressures using a Peter static tube, and there are two situations. In one case, the probe measures 20 kilopascal, that is static probe measures 20 kilopascal, that means static pressure is 20 kilopascal, and Petered probe measures 32 kilopascals. So, under this situation we have to find the Mach number and velocity, and in another situation the probe measures static pressure remains same, but the Petered pressure becomes 80 kilopascal. So, in that case what will be the Mach number and velocity. So, first thing we have to see that we have to recall these fundamental relations, that is isentropic relation which is stagnation pressure to static pressure, that is 1 plus gamma minus 1 by 2 m infinity square to the power gamma by gamma minus 1. Now, at this in this equation, if you put m is equal to m infinity is equal to 1, it will you can say that P naught by P infinity value is 1.89. Okay. So, I will say that this is the P naught by P infinity critical. So, critical value is 1.89. Now, let us see what we are actually measuring. So, first case we say case 1. So, for case 1 we are saying P naught is 32 kilopascal and P would be 20 kilopascal. So, P naught by P is, we can find out 1.6, that is 32 by 20 is 1.6. Now, you can, and this relations P naught by P will, using this isentropic relations we can find out. Okay. Now, here we can see that this P naught by P value is less than P naught by P critical. So, critical value is 1.89 and our value is 1.6. So, this implies that the flow is subsonic. So, we can blindly say that there is no shock wave. So, when you say there is no shock wave, then we can use this isentropic relations from this P naught by P is equal to 1.6, that is equal to 1 plus gamma minus 1 by 2 m infinity square to the power gamma by gamma minus 1. So, here putting gamma is equal to 1.4 and we can calculate n infinity as 0.8447. Now, once you, but we also require Mach number as well as velocity. So, velocity can be written as m infinity a infinity. So, a infinity can be taken as square root of gamma r t infinity, and this gamma r t infinity can be found out, and this value is r is equal to 287 joule per kg Kelvin. Gamma is equal to 1.4. So, from this we can find out A infinity as 346 meter per second. So, from this we have M infinity, we have A infinity. So, you can say V infinity would be 293 meter per second. Okay. Now, let us evaluate the case 2. So, in a case 2 we have P is same 20 kilopascal, but P naught is 80 kilopascal. So, ratio would be P naught by P would be 80 by 20, that is 4, and you see that this number is greater than P naught by P critical, which is 1.89. So, this will implies flow is supersonic. So, when you have flow is supersonic, for this particular pressure we can assume that if you have a probe and there will be normal shock. So, this will be condition 1, this will be condition 2, and what we measure is P naught 2, and what is your one condition is P 1. So, this ratio is 4. So, you have to use this now normal shock table. So, this is an extract from the normal shock table. For this P naught 2 by P is equal to 4. So, P naught 2 by P is equal to 4 means you have to refer this particular number, and from this this value falls within this number, and by interpolation of Mach number we can say this will give you M 1 as close to value of 1.65. So, when you say M 1 is 1.65, then we say Mach number we got, then velocity can be calculated, that is M 1 into A infinity. So, that is 1.65 into 346. So, this means B infinity is equal to 561 meter per second. So, through the measurement of static pressure and stagnation pressure, this particular problem tells us how you can evaluate the velocities in a subsonic flow and in a supersonic flow. Now, next problem we will deal with a temperature probe. So, by temperature probe we have to recall that we have 3 temperatures. One is, if you just recall our philosophy, that probe is insulated from the side and the sensing surface is only exposed to the flow. So, these are connecting wire, and if it is a supersonic flow, there will be a bow shock. So, the condition will be P 1, P naught 1, T 1 and T naught 1, and at this condition the probe temperature would be T p, or we can say T a w, and your true values is T naught 1. So, let me put as T naught, remove 1, T naught and T, P naught and P. Okay. So, what data that give is that we have a pitot probe that indicates 300 kilopascal and 60 kilopascal, and it is a supersonic flow. So, obviously, first check what we have to do is that from the data P naught by P is equal to 300 by 60, that is 6. For this pressure ratio we can take normal shock table P naught, and here it will be P naught by P. You can say take this normal shock table, and it is close to this number will be 2.05. So, this will give you can say Mach number could be assumed to be 2.05, which is close to this number and this row. Now, once you have Mach number, then we have to revert back our temperature calculations. So, two things that has given, first is probe recovery factor, and we have to give in adiabatic recovery factor and probe recovery factor 0.95. So, let me start with the probe recovery factor. So, Tp. So, by definition we can say probe recovery factor Tp is related to Tp minus T divided by T naught minus T, and that is equal to 0.95. Okay. And we have to find another relations for this Mach number. For m is equal to 2.05. So, we can write down this relation, isentropic relation, T naught by T is equal to 1 plus gamma minus 1 by 2 m square, putting gamma is equal to 1.4, m is equal to 2.05. We can say T naught by T is equal to 1.86. So, by putting this we can write Tp minus T divided by 1.86 T minus T is equal to 0.95. But Tp that we have given as 600 Kelvin. So, when you put it, we can find out temperature value is 330 Kelvin, and T naught can be found out 1.86 times of this. So, it is 614 Kelvin. Okay. So, this is how we get. Now, if you recall our next definition, that is adiabatic recovery factor, R, that is nothing but TAW minus T divided by T naught minus T, and this number is 0.72, and we also know, now we know T naught, we know T. So, we can put it, we can from this we can calculate TAW as 535 Kelvin. So, what we see is that here we have three temperatures. One is true temperature, true value. If I say true value, mean that we are using theoretical relations for m is equal to 2.05, right, and when we are using this, what measurement we say, your actual number will be, static temperature will be 330 Kelvin and total temperature is equal to 614 Kelvin. But what we actually measure by insulating probe, we measure TAW, that is equal to 535 Kelvin. We can see there is about close to 80 degree Kelvin difference in temperatures, but because there is a conduction effect. Now, by proper calibration, if you assume the probe recovery factor to be 0.5, so we actually measure Tp as 600 Kelvin. So, if you can see that the probe temperature, and by using neglecting the conduction effect due to the connecting wires, the probe temperature is close to the stagnation temperature of the flow, but the adiabatic flow wall temperature is not that significant with respect to the temperature measured by the probe. So, the very basic bottom line is that in addition to insulation, we must also take suitable measures for to nullify the conduction, the losses due to conductions. So, with this I will conclude for this discussion today. Thank you for your attention.